Hello guys, good day. So today we're going to talk about introduction to lasers. My name is Daniel Vicario. I'm a faculty member from UST. So let's have a discussion today, introduction to lasers. So this is the outline of my presentation. So we're going to introduce lasers, some components of lasers, laser emission, characteristics of laser radiation, biophysical interactions, and exposure limits and safety. So we know that laser actually stands for light amplification by stimulated emission of radiation. So it is an electromagnetic type of radiation, so it can range from the various spectrum of light. So as you can see here, lasers can be visible. It can also be infrared or ultraviolet types of laser radiation. So like all waves, electromagnetic waves have wavelength and frequency, and these are related following this equation. Speed of light, c, equals the frequency times the wavelength of radiation. And this light has an energy, and that energy is given by E equals hf, where h is the Planck's constant. So it is one of the fundamental constants in nature. So light can be treated as both wave and particle or photon. So the energy of a photon is given by this equation, E equals h, the Planck's constant, times the frequency of light. So take note that laser is on this range. It is part of an electromagnetic wave. So it's mostly on the visible part, but it can be mostly non-ionizing. So when you talk about ionization, it is the process of producing ions. It is the process of knocking off electrons from an element, from a molecule. So most lasers are non-ionizing, meaning it doesn't cause ionization, while some part of it, especially those near UV, UVC, or part of the UVB, are mostly ionizing types of lasers. So there is actually UV lasers, and there's even an X-ray laser. Mostly in research facilities in Europe, there are a lot of those X-ray lasers. But what we know commonly are those that are in the visible region. Okay, so this is your electromagnetic waves. The lower part here on the left have longer wavelength or lower frequency, means lower energy. But on this right side of the spectrum have higher energy, higher wavelength, higher frequency and shorter wavelength. Okay, so just a recall of your electromagnetic spectrum. So what are the components of lasers? Oh wait, what are the applications of lasers? So here we have in the laboratory, so in research labs, in medicine and surgery, in industry, construction sites, offices, and even in households we use lasers. So here you have some disco, and for entertainment purposes, sometimes they use lasers. So make sure that you avoid exposing yourself, especially your eyes, to intense and bright light source, bright laser. So make sure that you don't look directly into the laser. Okay. And sometimes, when you are buying your groceries, you can find that they're scanning the barcode. They're actually using some laser scanners there. Okay, so you can buy your food or your groceries. And here we use lasers to correct the cornea, do some laser procedures on the eye, and even surgery. So they use laser to cut some parts of the tissue to do some surgical procedures. So there's a lot of applications of lasers. Okay, oops. Now let's proceed to the components of laser. So what are the components of lasers? Okay, so you have the lasing medium, which is usually gas, liquid, solid crystal, and semiconductor. And you have to have the energy source, which are electrical, corriente, electricity, and of course the mechanical structure. So you must have your mirrors, this side and that side, and the support, and of course the lens to focus your light source or your laser. And the support is usually a table or the housing of the the laser, the device. So that is where your lasing mediums are. The gas, it can be gas, liquid, solid. And you have the mechanical structure. This is the reflecting mirror. And this part here on the right is the partially reflecting mirror. So partially it will reflect light and partially it will allow the laser, especially if the intensity is high enough, the laser will pass through. So it will go out of the device. Now let's proceed to the laser emission. How is it emitted? So here's a sequence of events of what is happening. So first you must have the electrons. They will be excited from the ground state. So let's say these are your electrons. So it is on your lasing medium, on the gas. So they will be electric in a way, like electrocuted or being sparked. So if there's electricity, the electrons will jump to a higher energy level. So they will be agitated, they will have more energy if you apply electricity, corriente. So if there's electricity, the electrons will jump to a higher energy level, they will gain energy. And when it returns to a lower energy level, the absorbed, the gain energy will be emitted as a photon. So like this photon here. And the same process will happen to other electrons. So there's a lot of electrons there, so there will be a lot of energized and go back to the ground state, and then so will produce a lot of light. And these energy levels have the same frequency, have the same light. Okay, so what are now the characteristics of this photon emitted? So they are monochromatic. When you talk about mono, it's one, single, chrome, color. So the radiation have the same color, the same wavelength, frequency, and of course the same energy. They also are highly collimated. So if you talk about the collimation and divergence of your light, the radiation is almost parallel, highly focused, with very little divergence at about 3 or 10 degrees perhaps. So they are highly focused. As you can see in the diagram here, they will diverge a little. So if you're going to point a laser, if the intensity is high enough, it can reach the cloud and it's pointed. But if you're going to focus a flashlight, the flashlight will diverge more as compared to laser. So laser are highly collimated. Okay, so it is coherent. So what's coherence? In coherence, it means the electromagnetic waves are exactly in phase, in time, and as well in space. So it means the maximum of a single light, and then another light, the maximum adds up. So they are going at the same maximum minimum in the space. Okay, so this will add up, right? But if you talk about out of space, they can cancel out, or if they're not in phase, they will just produce a bit-like pattern here. So but what we want are in phase, coherent, because they will add up and they will produce higher intensity radiations, more. Okay, so now let's proceed to the laser radiation biophysical interactions. So these are the biophysical interactions, and what are the biological effects on your right. So if you have a UV laser, these are the interaction. It's usually thermal, so umiinit yung natatamaan ng UV laser, and as I've said earlier, some parts of UV are ionizing, so they can destroy the element, the, the molecule. In a way, you will produce ions. Okay? And dito, pwedeng, di ba, alam natin, pag ionizing radiation, such as part of UV and X-rays, they can cause cancer. Di ba? So, pwede yun. Pag UV radiation, pag UVX laser ang ginamit. So, possible ionization and photochemical. So, in some way, if you're using UV, for example, the skin might be damaged, the chemistry might be damaged, so the color might change. And so what are the effects, biological effects? So erythema is the blackening, or the reddening, I mean, of the skin. There can be, related to the eye, no? Damage to the eye, photokeratitis, conjunctivitis, and cataract. So there can be permanent or temporary damage to the eye. So if you're using laser that are in a visible and infrared A, so infrared can be A, B, C. So A has a higher frequency, shorter wavelength than C. C has a lower frequency, longer wavelength. So visible to IR, infrared. So visible and IR mostly thermal. There's also photochemical and optical interaction. So what are the biological effects? So it might damage your retina. Okay? So you have to be careful not to look directly on your laser. Skin injury if the intensity is high enough. Now, how about infrared? IRB and IRC. Take note, you cannot see infrared, you cannot see UV. We can only see visible. So we have to be careful here. Infrared, like you might not see it, but if your eye is exposed to infrared laser, your eye might be damaged, but you do not know because you don't see it. So the main effect or biophysical interaction of infrared lasers are thermal, and there's also thermomechanical, especially for pulsed lasers. So what are the biological effects? Of course, it can damage your cornea, and of course, thermal injury to the tissues. So literally, it can burn your tissue, it can vaporize your tissue. So now, of course, we should not be exposed to laser if it's not necessary. Like, we use laser for dermatological, for optical, or in ophthalmology and in surgery, in medical procedures. But we should not be exposed to unnecessary exposure to laser. Now, there are limits to this, but there are classifications. So usually the exposure guidelines are provided by International Commission on Non-Ionizing Radiation Protection, or ICNIRP. So this is a more reliable source of information that we can get. So there are different public and occupational exposure limits, and these exposure limits depends on wavelength and time and the pulse duration of the laser. So it depends on the wavelength and the pulse, and so there's a lot of things to consider, which I'm not going to discuss. Okay. So there are classifications of laser for class 1. So these might be in the toys or in laser compact disc recorders. So this is usually eye safe, no risk groupings. So you can say it's not that dangerous, but of course you have to avoid. In normal circumstances, usually if the laser is pointed to the eye, you will avoid it, you will blink your eye, you will move your eyeballs. So there's a natural defense mechanism of your eye. But let's say you point it in your eye and you did not blink, so there's still a risk. So there's always a risk. So you cannot say no risk, but you avoid direct exposure to the eye. If your skin is hit by a laser, class 1, no worries, don't worry, it's okay. But for class 2, so category, hazard classification, class 2, visible lasers with very low power, less than 1 milliwatt, it is not hazardous to the eye if the exposure time is less than 0.25 seconds. So if it's 1 second, you should be careful, do not point lasers into your eye. So examples of these are supermarket checkout scanners, laser pointers, and alignment lasers. So alignment lasers in industry, in construction, and even in medicine, we do use alignment lasers for like setting up a patient for for treatment or for diagnostic purposes. Class 3, it can pose a hazard to the eye. No hazard to the skin for incidental exposure, but perhaps for prolonged or higher intensity. You might expect damage to your skin, but usually no hazard for incidental exposure. So examples of these are in research applications, in military laser range as laser range finders. Now let's go to the higher or the highest level, the class 4. So these are hazardous already. It poses a potential fire hazard, significant skin hazard, or a diffuse reflection hazard. So the average power is greater than 0.5 watts. So examples of these, the lasers that we actually use for medical purposes, like all surgical lasers, in material processing lasers for welding and cutting. So these lasers can literally vaporize a tissue, a metal. It can vaporize a metal. Okay, so these are dangerous lasers. So it has to be used by people who are trained, who are skilled, and know how to use it properly. The ophthalmologists or the surgeons who have trainings on how to use it, so they are qualified to use it. Okay, so let's have a review. So this is the components of a laser. You have the lasing medium, the reflecting mirror, and the partially reflecting mirror. And how to produce laser: you excite the gas or the lasing medium here. The electrons will be excited, and when they will jump to a higher energy level, they will be agitated, more energy. But when they go back to their ground state, they will emit the absorbed energy as a form of photon. And those photons have the same frequency, same wavelength, and they will add up, and then they will produce even more intensity, and then they will come out of on this part on the right side of the partially reflecting mirror as a monochromatic, coherent, and highly focused light. These are some of the references. The pictures are taken from the internet, mostly from Wikipedia. So thank you very much, guys, and hope you learned something from our discussion about lasers today. So bye-bye, choose, see you in the next video.